Hi, folks. All right, getting into this chapter 14. I got my soundtrack. We're gonna get cooking here any minute. Just gonna get my notes together here. All right. Oop, let's see. Okay, put that away. I love me some Rubble Bucket. I could listen to Rubble Bucket all day. All right, let's get this thing going. So, first lecture, chapter 14. So as you can see, I'm going to go by sections in the book. So at any point during these little mini lectures, if you get lost, take a look at, this section in the book. It's a pretty short section. That's why I'm kind of dividing these up into these little mini lectures. And then you can read more on the book if this lecture doesn't do it for you. Okay. So let's get into it. Chemical equilibrium. So we'll start by talking about a fairly common reaction here. This is called water-gas shift reaction. You don't need to know that. And you'll notice that we've got a new kind of arrow that you haven't seen before. Okay, so that's an equilibrium arrow. And it shows that there is a forward reaction, but it also shows that there is a reverse reaction. So in other words, in these equilibrium reactions are reactants, in this case, steam and carbon monoxide, can go on to form products. However, when a significant amount of those products form, now H2 and CO2 can react with each other and go backwards as well. Okay, and so equilibrium is achieved when the concentrations stop changing over time. So let's see what this graph is telling us here. So on the y-axis, okay, that's concentration. And typically, we're going to always work in molarity, right, in mole per liter. And on this x-axis, this is showing us time. Now, eventually, we will get into chemical kinetics, where we're going to, the only thing we'll talk about is just how chemistry evolves in time. But for now, we're just kind of going to gloss over this particular subject. And we note here that in red, we can see that these would be our reactants. Okay, oops, let me try to write that again. All right, and in blue here, this is our products. Now, I just talked about how this, these reactants can react forward into making products, but then these products can also function as reactants and work their way backwards to products. So when we see this graph here at time 0, our reactants are the H2O and CO, and our products here are the H2 and CO2. Okay, so you can see at time 0, we have some amount of H2O and CO, and we have 0 H2 and CO2. And as the reaction evolves in time, the reactants decay and the products evolve. But you can see what happens is they eventually hit this point where their concentration stops changing with time. And that is when we have achieved equilibrium. Okay, when the concentrations are no longer changing. All right. Okay, so there's another way that we can think of this. If we separate these two reactions out here, and now I've got them separated as the forward reaction where that H2O and CO makes H2 and CO2. And then I've also written it as the reverse reaction, and I wrote it, moving to the left so that we recognize when we put this together, it's our equilibrium reaction. Okay, and so we noted chemical equilibrium is defined as the state where the concentration of all reactants and products remain constant. So this is just another way we could think of this. So if, once again, my x-axis is time, and now in this representation, my y-axis is the rate of reaction. So I often write RXN as an abbreviation for reaction. And so this rate of reaction would be expressed in molarity, let's say per second. Okay, it could be molarity per hour or molarity per minute, but we recognize this is a rate. Much like when you drive your car, you're going so many miles per hour, right? Well, chemical reactions can proceed at rates of so many, molarity per second. Okay, and so once again, the red is reactants, in this case, the H2O and the CO. And the blue line are products, once again, in this case, the H2 and the CO2. And you notice here that the rates are not constant, which you might have guessed that from these profiles, right? For those of you that have taken calculus, you might recognize the slope of these lines changes over time. Calculus is not required for this class, so if you don't understand that just yet, that's okay. And again, we're going to come back to talking about kinetics soon. But what you can see from this as well, the rates will eventually become equal. Okay, and so when the rates become equal, also that will lead to constant concentration over time. So equilibrium has been achieved.